let's go over this, okay? Anyway, study this problem. We've also done two other similar problems today in today's lecture. Make sure you understand these. Yeah, you just
we got 21.7%.
I haven't done the calculations, but sure, let me do the math here. .2206. Oh no, .2177.
Yes.
Okay, so let's check our conditions. All right, first of all, was our sample selected randomly?
Yes.
Okay. Is our population big? Yes. Okay. So again, I did not specify the size of the population, but in some cases I don't need to. All right. We're talking about a sample of college students, which we would expect to be representative of all college students. And can we assume that all college students, there's more than 600 of them? Yes. Okay, large sample condition, is that met?
Yes.
Okay, so our n is equal to 60, and p is 0.55. So 60 times 0.55 is equal to 33, is that right?
Mm-hmm.
And then n times 1 minus p is equal to 27. Both of those numbers are bigger than 10. So our three conditions are met. That's good. We're taking a random sample of 60, and I want to know what's the probability that I'm getting less than half of them living in an apartment. So I'm asking, what is the probability that p hat is less than 0.5? Okay, my sample proportion is less than 0.5. We know that p hat comes from a normal distribution. And the mean is equal to p. And my mean, so that would mean my mean is equal to 0.55. And my standard deviation, sigma, is equal to the square root of p times 1 minus p over n. My standard deviation is 0.55 times 0.45 divided by 60. I get a standard deviation of 0.0642. Okay. There was a question? I thought I heard a question, but maybe not. Okay, so I have my mean and standard deviation. I just want to make sure that's okay with everyone.
But those are two different problems, right? That's asking one thing and then you're asking for the probability, right?
No, it's all the same problem.
Oh, yeah.
We have to check our conditions, and then we're going through the problem. Okay? This is the same question. What is the probability that p hat is less than 0.5? That is what this is asking. We take a random sample of 60 college students. What is the probability that less than half of our sample live in an apartment? That I'm just interpreting this question into something with the symbols p hat less than 0.5. These two questions are the same question. Okay, so what do I do now? I get a z-score. So my z is equal to 0.5 minus 0.55, and I'm dividing this by 0.0642. And I get negative 0.78.
you rounded it towards the end?
Yeah, so, I mean, if I,
You got 0.778 you were trying to.
yeah, we've got negative 0.778, alright? But when you look it up in the z table only has 2 decimals. So you have to round it off to 2 decimals, okay? When using the z table, there are only 2 decimals. So we use z equal to negative 0.78. So when I look up negative 0.78 in the table, I get the area to be 0.2177.
It's negative, right?
So is that my answer, or do I have to subtract that from 1?
It's not negative.
This is my answer. What is not negative?
My answer's not negative 2.
My z-score is negative 0.78, but my answer is 0.2177. My answer is a probability, right? The question is asking,
Okay.
what is the probability? So my probability always has to be between 0 and 1.
If it wasn't equal, like if it wasn't bigger than 10, then we wouldn't be able to find the probability, right?
Right, if
Okay.
the conditions, if any of those 3 conditions were violated,
Then we just
we cannot proceed with the problem, okay? Because we cannot use the normal model. Yeah, Mark?
How come you're not subtracting it by 1?
Because I'm asking, what is the probability that less than half? So am I shading to the left or to the right of 0.5?
To the left.
I'm
So
shading
if
to
you
the
were,
left.
so if you were to say, what is the probability that more than 50%, then you would subtract it by 1.
Yeah, so if the question says, what is the probability that more than half of our sample is in an apartment? Then yes, I would have to subtract that area from 1.
over
No, no, no.
this.
If it says
You got that from the.
it says less than less than subtract 1 by
Wait, so if you were to ask us probability that we're greater than, we just do 1 minus that number?
Yes. Yes.
And would you ask us for the area, you wouldn't ask us for the distance in between for the problem like
I
this?
mean, I don't have that kind of problem written on the quiz, but if I did write something like that, you could answer it, right?
Yep.
If I said, what is the probability that our sample has between 50% and 60% people living in an apartment, you could answer
You
it.
just solve for both.
Yeah, it would be more work, but it's definitely something you know how to do, or you should know how to do. Okay, we will continue on. So the final topic for the day is called confidence intervals. Listen up. With a confidence interval, we are going to look at a sample, and based on what we see in the sample, we want to make statements about the population. Okay? So let's say this time I've got a giant bucket, not of M&Ms, but maybe, I don't know, Skittles.
Taste the rainbow.
And I'm going to take a scoop of Skittles. Alright, this time I don't know how much of, what the proportions in the Skittles are. Okay? Let's say my favorite flavor in Skittles is red. Okay? All right, maybe there's so we want to know what percentage of the bucket is red. Okay, we don't know. But let's say I take a scoop of 200 random Skittles. And let's say my scoop has has 34 red Skittles in it. So my sample proportion P hat is equal to what? Is that okay? So I took a scoop of 200 Skittles, and 17%, or 34 out of 200 were red. So 17% of my scoop was red. If I were to then go into the bucket and count all of the red M&M, or not red M&Ms, red Skittles out of the bucket and calculate that proportion, what do we think the proportion in the bucket is?
Similar to that.
Yeah, so we don't know exactly what percentage of the bucket is red Skittles, but we would expect something around 17% to be red Skittles. Does that make sense?
Yeah.
When we look at the bucket, or the population in this case, it probably won't be exactly 17%. But we expect something close to it. Alright? So what can we say about the population? Well, we're going to give ourselves basically some buffer here. And we're going to say, well, when I took 200 Skittles, 17% were red. Okay? So when I talk about the population, I'm going to say it's probably 17%, give or take 3%. Okay, I'm just making up that number 3%. But I might say the population is probably about 17%, give or take 3% red Skittles. Okay, so I could say something like, based on my sample, I think the population is about 17% red, give or take 3%. Okay? So that's basically saying, I think the population is between, what, 14% and 20% red. Okay, and 14% is 0.17 minus 0.03, and this is 0.17 plus 0.03. And so this is what we would call a confidence interval. We're giving ourselves a range of the proportion in the population, and that range is based on what we see in the sample. So if our sample was 17%, we'd say it's probably around 17% plus or minus, or give or take some value, 3%, or some other value. Okay? This is called a confidence interval. Okay, so I have a confidence interval. So my confidence interval goes from 14% to 20%. Does that make sense? Okay. Could the bucket of Skittles actually be 21% red?
Yeah.
It could be, right? But we're just, based on what we see in our sample, we're creating a range, and this is what we're kind of estimating or guessing what the population is like. The population could be 18%, which means our confidence interval is correct, because 18% is between 14 and 20. But our confidence interval could also be wrong in that the population maybe is actually 21% red, and then our confidence interval is wrong. Okay? But we're going to learn how to pick this number, the give or take amount. Okay? And when we follow the rules for selecting that amount to give or take, we can get an idea of how often our confidence interval should be correct. Okay? But that's the idea behind the confidence interval. We don't know what exists in the population. Okay? This bucket represents the population. We don't know what exists in the population. But we take a scoop or we take a sample, we can see what's in the sample. And based on what we see in the sample, we're going to try to make a statement about the population. Yes?
You chose 3% as random.
I picked it just as an example for this class because 3% is an easy number for us to deal with here. Okay?
It's usually between. Is it?
Okay, so we'll go through the rules on how to get that actual number. There's formulas makes it a little bit more complicated, okay? But the concept is the same. You see something in your sample proportion is p hat. That's going to serve as kind of your central point, right? If we had to guess what proportion, if I said, just give me a single number estimate for the proportion in the sample, you would use not in the sample, in the population, you would use 17%, right? Because this is what we saw in the sample, okay? But to kind of give ourselves some buffer, we go plus or minus some value. And here in this example, I picked 3%, but it's really, we're going to use a formula to get the actual value to use. Okay? So when we make a confidence interval, we are making a range of values for P, the proportionate population proportion. Based on what we see in our sample. So the general form for a confidence interval is that we use p hat, our sample proportion, as the center of our number. Okay, this serves as the center, the sample proportion. And then we go plus or minus. So over there I did 17 minus 3% and 17 plus 3%. I'm combining the plus and the minus into just one symbol here. Okay, plus or minus, and we'll call this the margin of error. And the formula for the margin of error is going to be z star times p hat times 1 minus p hat over n, okay? So this part is called the margin of error, okay? It boils down to a single number like this. So over here, my margin of error is 3%. Okay? But this is the formula for getting the margin of error.
Wait, so you have plus or minus z times the square root of that?
Yes. Okay? So this is the formula for how we get the margin of error. Okay? But the margin of error, don't get scared, is just a number. Okay? It might be something like 3%. But to calculate how big our margin of error should be, we have to use that formula. Okay? But again, don't lose sight of the big picture, which is just what percentage of the bucket is red Skittles. It's going to be something around 17%, give or take 3%, or give or take some number. That number is called the margin of error. And you've heard that term margin of error before, right? A lot of times during election season, they'll say, you know, candidate ABC, you know, has a lead with 52% with a 2% margin of error or something like that. Okay? So that, you know, we've heard these terms before. And that's all that we're doing. Okay, so yes.
So for example, margin of error will always be a given test, for example, or do we have to?
No, you're going to have to calculate the margin of error
Okay.
yourself, okay? But p hat, we know how to get. What is p hat?
Population.
No, p hat is our sample proportion, okay? So if you have the sample proportion and n, what is n?
Size.
Sample size, we can get this part of the margin of error, okay? The selection of z depends on how confident we want to be, okay? So if I'm saying, if I want to be really confident that my interval has the true proportion of red Skittles, would I do 17% give or take a small amount, or 17% give or take a large amount?
Large, small,
I want to be really confident.
small.
No, I'm going to use a large amount because I want to make sure that I'm getting the true value of the proportion of red M&Ms, or red Skittles. Okay, so if I could say, you know, I'm very confident that the proportion of red Skittles is 17%, give or take 10%. Okay, and so that means any value between 7% and 27%. I'm saying the amount of red Skittles is somewhere between 7 and 27%. And I can be very confident about that, but it's such a huge range that it's not very useful. Okay? If I'm willing to give up some confidence, I can make a smaller range, but I'm more likely to be wrong as well. Okay. So this is a set of, I'm going to give you a set of numbers that you either need to memorize or make sure you have written down on your note sheet. Okay? These are the values of z. Z star, okay, depend on the confidence level. Okay. So if you want to be 90% confident, or we'll start off with 80% confident. And then we have 90% confident, 95%, and 99%. So these are 4 numbers you either need to memorize or make sure you write down. 80% is 1.28, 90% is 1.645, 95% is 1.96, and 99% is 2.58. 2.576, but 2.58. So make sure you either learn these, memorize them, or write them down on your note card for next week's quiz. don't come to me saying I forgot to write these numbers down and I don't know how to answer this problem. I'm warning you. You gotta know these.
Oh,
Yes.
what about like lower than 80%, like 80, like,
So we generally don't make confidence intervals much lower than 80%.
what about 85%?
Okay, so yes, we could make an 85% or a 93% or something, but these are probably the most common values for confidence interval. So these are the only ones I'm going to require you to know. Okay. All right, so let's try making a confidence interval. Okay, so let's say we take a scoop of 200 Skittles, 34 are green, or I'm sorry, are red. 34 are red. Let's make a 90% confidence interval for the proportion of red Skittles in the bucket. Okay, so my p hat is 34 over 200. I'm getting 17%. If I'm using 90% confidence, what is my z star? 1.645, or 90% confidence. Okay, and then this part, this is we call this the standard error. It's going to be 0.17 times 1 minus 0.17 divided by 200, my sample size. I get 0.02656. Is that okay?
What does SE?
SE stands for the standard error.
Okay.
SE so the margin of error consists of the standard error and this Z, we call this the critical Z.
You're gonna provide us with the Z, right?
Now I told you that you need to know these four Z's, okay? You need to know these four values for Z. And your choice of Z depends on what level of confidence you're using. Okay, so let's put everything together. P hat plus or minus Z times the square root, or the margin of error, times standard error. So I have 0.17 plus or minus 1.645 times 0.02656. So here I have 0.17 plus or minus 0.0437. Okay, we're just going to round off to 0.044. So if I want to be 90% confident about the proportion of Skittles that are red in the bucket, I would say it's around 17%, give or take 4.4%.
Do you want us to add the percentage?
Yeah, we can do that also. Okay. So 0.17 minus 0.044 is 126 to 17% plus 0.044 is 0.214.
Are we going to be going back to percentage?
Huh?
Are we going to be going back to percentage 12?
Yeah, you can, if you want to do that, that's also fine.
That makes more sense in the equation.
12.6% to 21.4%.
Yes.
Okay? So, at the end of, after looking at 200 red Skittles, 200 Skittles, and finding 34 of them are red, what can we say about the proportion in the bucket that's red?
12.6 to 20.
Yeah, we'd say I'm 90% confident, because that's our level of confidence. I'm 90% confident that the bucket is between 12.6% and 21.4% red. That the bucket or the population is between 12.6% red and 21.4% red. So that's a confidence interval. It's a range of values that we think are plausible values for the amount in our population, or in this case, how much of the bucket is red. Okay. Again, to recap, the idea is we don't know how much in the bucket is red. We start off with that. We don't know how much in the bucket is red. So we take a random sample. We've taken a scoop of 200 Skittles. We looked at this sample of Skittles, and we see that 34 of the Skittles are red, which means 17% of my sample is red. So based on what I see in my sample, what can I say about the bucket, or what can I say about the population? Well, we go through the formula, and it turns out that our guess for the amount of red Skittles in the bucket is going to be 17%, give or take 4.4%. So that means at the end of the day, I am 90% confident that the bucket, or the population, is between 12.6% red and 21.4% red. Could the bucket actually be 23% red?
Yes.
It's possible. But if the bucket is 23% red, then that means something weird happened when I selected my random sample of 200 Skittles, because 200 Skittles ended up only being 17% red. So that was something a little unusual. But is it possible? Yeah, it's possible. Yes.
If you're saying that 99% confident that the population stays between 12.6 and 21.4, can you say it's still possible to be at 30?
Yeah, even so, when you're 99% confident, you're creating kind of a bigger range. But yeah, it's possible that the population is still outside of that. Okay, you're more confident because you're creating a bigger range for yourself. But is it possible? Yeah, you could still be wrong. Okay. It's kind of like let's say you're playing a game and someone's going to toss a ball up in the air, okay? And your job is to draw a circle on the ground where you think the ball is going to land, okay? You could draw a small circle, okay? But you won't be very confident that the ball is going to land in that circle. You could make a very large circle, and you are more confident that the ball will land in the circle, but it's still possible that the ball lands outside of the circle. Okay? And that's the similar idea here. You could make a really large interval, but it's possible that the population proportion, or the percentage of Skittles that are red, or whatever we're looking at, is still outside of the range you created. But by making a larger circle, or a larger interval, you're more confident about that interval. Is that okay? If I change from 90% to 99%, what changes in my formula here?
I'm sorry, what's the question?
So if I'm, instead of making a 90% confidence interval, I decide to make a 99% confidence interval. What changes?
Yeah.
The only number that changes is instead of 1.645, I'm going to use 2.58. And so my confidence interval gets larger. Okay?
Does that mean it's just like a larger like ratio? It would be like, for example, it would be like, I don't know, like 10 to
Yeah, it'd be like
25.
10% to 25% or something, right? Okay. I don't know. Some other number. Okay. Let's, I want to talk about how we interpret the confidence interval, just to make sure we understand it well. Okay. So the idea over here was we're taking a random sample of Skittles, and based on what we see in our sample, we're making a conclusion about the population of Skittles, or the bucket of Skittles. What if I'm taking, let's say I take a random sample of students at a high school.
Is this a new example?
This is a new example, okay? I'm just asking, I take a random sample of students at a high school and ask if any of them have smoked cigarettes. If they have smoked cigarettes. Is it illegal? It's illegal to sell cigarettes to an 18-year-old, but is it illegal for, someone under 18? Is it illegal for a minor to actually smoke? Is that?
Yeah, it's
That's
illegal for
We'll
minors.
get
So it's illegal to smoke and it's illegal to purchase and things like that. Okay.
It's
Well,
illegal to smoke
but
publicly.
some people still break the law. All right. Okay, so. Let's say we ask 160 random students. And 25 have smoked. I don't know, maybe that's too low or too high. I guess it depends where you ask. Okay, so anyway, before we get into the answer, whatever our answer is, let's say we make a 90% confidence interval. Okay. When you make a 90% confidence interval, you go through the formula and you're going to get some number to some number. Okay, a low number to a high number, right? You get your proportion plus or minus something. You get from here to there. Over here was 12.6 to 21.4%. Okay? So let's say we've gone through that process. I want to talk about the interpretation. We would say I am 90% confident what? That between, or that the proportion of what? That the students at this high school, that this selected high school, right? Because this is a random sample of students from a certain high school. So this sample can only be representative of this population, which would be all of the students at this high school. Okay, so I'm 90% confident that the proportion of students at this high school who have smoked is between blank and blank. So getting the numbers and knowing the interpretation are equally important, okay? You have to be able to tell me what these numbers mean, okay? You can't just say, here are these two numbers, ta-da, okay? You gotta be able to put it into some context here. Everything we do in this class has some kind of meaning. At least the results have some kind of meaning. Okay, so go ahead and try to find the 90% confidence interval, the numbers behind it. Alright, what is p hat?
I see it.
P hat is 25 divided by 160, 0.1565. P hat is our sample proportion. What is our z that we're using?
1.645.
1.645, we're making a 90% confidence interval. Our standard error, this part turns into, so 0.15625 times 1 minus 0.15625 divided by 160.
Professor, you be able to round it to 0.16?
I would leave at least 3 or 4 decimals. Okay. I'm getting 0.0287. Plus or minus. At the end, you can round off to 3 decimals or something.
So you don't round it off, because what I did is I round it off to 0.16 to get 25 over 60, 160.
I think you run into some risks there, rounding so much.
Just always make sure to